Hello, everybody. So we've talked about some of the different ways of finding distance. We said that the very best way is to use parallax, and I can see how that star shifts, and I can very easily calculate how far that is from us to that star. The disadvantage is it has to be fairly close by, 200 parsecs or so. We've talked about how we can use standard candles. So one example would be a Cepheid variable. The Cepheid variable we can detect all the way out to maybe 25 million parsecs, which is a long way, but it's not to the edge of the universe. For anything else beyond that, we really kind of have to get lucky and see a type 1 supernova, but those just don't happen very often. So figuring out the distance to the edge of the universe, to the most distant galaxies, is actually pretty challenging. Fortunately, there is another way. So that's what we're going to look at today is Hubble's law. Edwin Hubble, when he discovered this, basically gave us a way of estimating the distances to these very, very distant galaxies and the ones that are close to the edge of the universe. Now, we're not getting just a precise measurement, but it's at least giving us a ballpark estimate. So that's what we're going to look at today. Let's get started. All right, so we've talked about finding distances. We've talked about finding large distances. Now we're going to talk about finding very large distances. And by this, I mean literally to the edge of the universe for this. So make sure that you've got Tool 28 out. Looks like this. And pause the video until you're ready to go. All right, so Hubble noticed that when we look at the spectra of all these galaxies out there, practically all of them, except for the ones just very close to us like Andromeda and such, practically all of them are redshifted. Well, if they've got redshifted lines, what does that tell you? Are they moving towards you or away from you? Redshifted means they're moving away. So that means everything in the universe, more or less, is moving directly away from us. Does that mean we're in the center of the universe? Does that mean we smell bad? I don't know what it is. But when we look at these two particular lines that you see here, this is the hydrogen or the calcium K and H lines. So you see that the further out we go, the farther away that galaxy is, and this is increasing megaparsecs here, the more that line gets shifted over. So what Hubble did was he plotted the recession velocity, that the measurement he got based on how much the line had been shifted. So he just used the Doppler formula, same thing you guys know how to do. And then he plotted that against the distance. And he got the distance by looking at type 1 supernova. Oh, I'm sorry, by looking at these two were type 1 supernova, but for most of these, this was looking at Cepheid variables. So when he did that, he saw that everything fell right on this beautiful straight line. Well, you may remember from high school what the equation of a line is. It's y equals mx plus b. B is the intercept, which happens to be at 0 right here. Y then is the y-axis, x is the x-axis, and m in this is the slope. So what Hubble said was, okay, well, this actually does cross at the origin, so our y-intercept, our b, is going to be 0. So I'm left with y equals mx. He said my y value, the y value here, is going to be the velocity. The x value here is going to be the distance. And so he said, okay, v equals md. And m is the slope. He said, well, that's a constant because the slope doesn't change, so I'm going to name that after myself. Yeah, that's the ticket. And that is honestly how a lot of these physical laws that you've been studying, how they were found. They plotted two things together, they saw that there was a constant, said named it after themselves, and then they were famous. And you could do that too. So this H0 is called Hubble's constant. The whole law, V equals H0D, is called Hubble's law, but you guys know there's nothing special about it. It's just the equation of this line here. Same thing you did in high school. So Hubble's constant has been measured, and it varies depending upon who you're talking to. And like I said here, anywhere between 65 and 75 has been found. So it's not as constant as you might want to think. The current best estimate is about 67.8. The units of that are kilometers per second per minute per parsec. We don't have to worry too much about that. We just need the number here. So let's see how we would use this then. So we've got an example here down at the bottom. So the rest value of the hydrogen line is 656.3 nanometers. So we're looking at that far right reddest hydrogen line. Let's say that we measured it to be at 665.1 nanometers. So speed, we want our answer in kilometers per second, so we're going to use 3 times 10 to the 5th, and we'll use the Doppler formula to figure that out. So let's do that. So first thing we need to do, so remember I need to find the shift. Well, that's going to be the rest wavelength and the observed wavelength, so observed minus rest, gives me 8.8 nanometers. The rest wavelength then was 656.3, and then C, we said we were going to use 3 times 10 to the 5th. So let's put that on our calculators. So I do 8.8 divided by 656.3, and I get 0.0134 times 3e5, and so I get 4,023 kilometers per second. So that's how fast that galaxy is moving away from us. Now, I want to make a quick note that in the lab, you could use any line for this, and we'll often use the K and H lines just because they're ones that, even at the edge of the galaxy when they're so far shifted that the 656.3 line would be gone, we can still see the K and H lines. Doesn't matter. The only thing that's going to change is what my rest wavelength is. I still want to measure the shift, count those tip marks, multiply by the size of each tip mark, and that'll give you the shift. So use the shortcut way. I think you'll find that a lot easier. All right, so to get the distance using Hubble's law says V equals h0 over d, but I know V and I know h0, so what I want is d. So I want to get the d by itself, so I'm going to divide both sides by h0. So I get d is V over h0, and you just plug it in. We got 4,023 with the first one, and so then we divide by 67.8, which is Hubble's constant from the previous slide, and I get 59.3 megaparsecs. So that galaxy is 59.3 million parsecs away. If you need to convert it to parsecs, you just multiply that by 1,000,000, and then that will be your final answer. Hubble's law, though, because of the units here, will always give you your answer in megaparsecs. It also always needs the speed in kilometers per second. Make sure you make that conversion, it's important. Well, okay, so if everything is moving away from us, does that mean we're at the center of the universe? I mean, we spent thousands of years trying to prove that we're nothing special, that we're not at the center of the universe. Yet here it looks like everything is moving away. Well, in reality, the galaxies aren't really moving at all, much. So space itself is expanding. Space-time is expanding. And so if you think of the universe as being a balloon, space-time as being a balloon, and it's only the surface of the balloon, so don't carry this model too far. There's nothing in between, there's nothing outside. Everything that exists is on that surface. And let's imagine each one of these coins is a galaxy. If space, the balloon, is expanding, do you see that all of these coins will get farther and farther away from each other? No matter where you're standing, let's say that I'm at this one in the middle, okay, we can agree that it looks like everything's moving away from me. But let's say I'm standing on this coin right here. From this guy's point of view, everything's moving away from him. So there is no center because no matter where you are, everything looks like it's moving away from you. See if you can follow through that. So if I'm looking at the penny here, for example, this one, as the balloon blows up, the penny thinks he's standing still and everybody else is moving away from him. So Doppler shift isn't really what's happening here. The red shift isn't really because these galaxies are moving. They are moving a little bit on the balloon, but not much, not compared to the expansion of the balloon. What's happening is as space expands, the wavelength that we receive is getting longer. And so you see that here I've still got a grid, but my grid is getting bigger. And so that's making my wavelength get longer and longer and longer. And you guys know that a long wavelength is redshifted. So what we're measuring when we're measuring the shift in the spectrum of these lines is the light has been stretched because of space's expansion. And the more space is expanded, the more it's been stretched. Well, remember, I'm looking back in time when I look at these galaxies. So I'm seeing a longer period of time over which that light was stretched. So if space is expanding, then if I run the clock backwards, everything must have come down to an initial point. And this idea was actually mockingly called, what, you've got some sort of big bang there, and that's what you say the universe was created from? Because for over 100 years, more than about 100 years ago, we thought that the universe was just constant. It never changed. It had always been here. It was always going to be the same. And the idea of the universe having a beginning is kind of a problem for a lot of people because, what happened before the beginning? Well, science can't say anything about that because space and time were invented during that time. So we'll talk about that when we talk about the birth of the universe. But, for example, somebody asked St. Augustine, well, what was God doing before he created heaven and the earth? And he said, well, he was making hell for people to ask stupid questions. He may know more than we think. So, but one way or another, we can't go before the Big Bang. If everything is expanding outward, if we go back in time, everything must have at one point been right there in one little point. Now, the question is, people ask me, well, where did the Big Bang happen? Well, the answer is everywhere. Remember, the whole balloon shrunk down to a point. So everything was inside the universe. There was nothing outside of the universe. So that bang then was the whole universe expanding, and you were inside it while it was expanding. When we figure out how long ago it was, if we know the distance to a galaxy and its velocity, then, so let's say I know how far it's traveled, and I know how fast it's going, then I can figure out how long ago it left. And think about it, this makes sense. Let's suppose it's 120 miles to Tucson. Okay, it's not, but let's pretend that it is. It's 120 miles to Tucson, and you are traveling 60 miles an hour, and you arrived in Tucson. How long ago did you leave? Well, if it was 120 miles and you were traveling 60 miles an hour, 120 divided by 60, you left 2 hours ago. So that's the exact same thing we're going to do with the age of the universe here. We'll find a galaxy, any galaxy, farther out is better, and then see how fast it's going, know what its distance is, and then just do distance divided by the velocity. So that will give us the age of the universe. So let's figure it out. So let's take this galaxy that we just did. We said that it had a velocity of 4,023 kilometers per second, and its distance was 59.3 megaparsecs. Now wait, I can't just put these in here. I've got to fix my units. I've got to convert my distance into kilometers so that the kilometers will cancel and I'll be left with seconds. So let's convert the distance into parsecs to start off with. So this is 59.3 megaparsecs. So one megaparsec is 1 million parsecs. So 1e6 parsecs. So I want my megaparsecs to cancel. So I'll put the megaparsecs in the bottom, parsecs in the top. 1 goes with the megaparsecs. 1 times 10 to the 6 goes with the parsecs. Multiply by everything in the top, divide by everything in the bottom, and I get 5.93 times 10 to the 7 parsecs, which is the same thing you would have gotten if you had taken this and multiplied by 1,000,000, but now you know why. Now, though, if I want to convert this distance into kilometers, so take what I want to convert, this is in parsecs, and I know that 1 parsec is 3.09 times 10 to the 13 kilometers. If you're wondering where we get these constants from, I've uploaded an equation sheet that has all of the constants and conversions in it. So doing the math then, 5.93 times 10 to the 7, so 5.93 E7 times 3.09 E13, divide by 1, which of course isn't going to change anything, and I'm left with that galaxy is 1.83 times 10 to the 21st kilometers away. All right, so let's take those values and let's figure out the age of the universe. We don't do small questions here in astronomy. So T then is going to be the distance in kilometers, 1.83 times 10 to the 21st kilometers, divided by 4,023. Let's put that in our calculator and make sure that it works. So 1.83 times 10 to the 21 divided by 4023, and I do get 4.55 times 10 to the 17 seconds. That's a lot of seconds. But that's how old the universe is in seconds. Now that's a little hard for most of us to relate to, so it's probably be a good idea if we converted that to years. So here we've got 4.55 times 10 to the 17 seconds. I want my seconds to cancel, so I'm going to put seconds in the bottom. There are a lot more seconds in a year than there are years in a year. So 3.15 times 10 to the 7 seconds in 1 year. And if you're wondering where we get these constants, I've uploaded an equation sheet to Canvas that has all of the constants and conversions and everything in it that you need. So there's about 31 million seconds in a year. So these will cancel out, multiply by everything in the top, divide by everything in the bottom. So let's make sure that we get what we're supposed to here. So 4.55 times 10 to the 17 times 1, it's not going to change anything. Divide by 3.15 times 10 to the 7, and I get 1.45 times 10 to the 10th years. So in other words, the universe is 14.5 billion years old. You just measured the age of the universe. All right, so you'll get more practice with this on the practice sheet and then also in lab. And as always, if you have any questions, make sure that you're coming to see me. So Hubble's law is very important because it allows us to get an estimate of the distance to things that, we just have no other way of doing it. Because of this constant acceleration or this constant expansion of the universe, we can figure out, well, okay, if I know how fast it's moving now, I know how long the universe has been expanding, and so I can figure out how far it is based on its speed. There are some issues with this that we're going to get into in the next lecture when we start talking about cosmology and dark energy. But as a first approximation, it works really well for us to figure out, well, okay, is it millions or is it trillions or however many light years away this thing is? So this is an important technique, and it's kind of the top part of our distance ladder from everything that we've been working with, starting with parallax and building all the way up to Hubble's law. So now you know how to find the distance to the edge of the universe. We'll see you next time.